be possible. Okay, so our last unit is on something called power. One of the reasons why I break the units up the way that I do, you guys ready? The way the textbook organizes things and the way most teachers organize things is they usually put energy together with another section, usually with some of the circular motion stuff. I like to make anything that oscillates, goes in a circle, or goes in a wave, I put it all together in one unit. But most other teachers usually take one of those three things and combine it with energy. I don't, and one of the reasons why is that everything that we do in the energy unit, for the most part, is actually a review of either grade 9 or grade 10 science. And this last topic on power, believe it or not, is actually in grade 9 science. I just finished teaching my grade 9s last semester. You may not remember this. Like the last two groups that I taught this to this morning, some of them were like, yeah, maybe I remember power. But like in theory, this is actually a review of a grade 9 concept. And so that's one of the reasons why I like to put energy together in a small section, is that most of it is supposed to be a review of previous units. So whether or not that helps you or not, I guess, is an individual thing. So let's talk about power. The word power, from like a English language point of view, power gets used for almost everything. We talk about power when we talk about someone's strength. We talk about how like the president of the United States has a lot of power because he has a lot of influence. The military has a lot of power. Police officers have the power to give you a speeding ticket. They have authority. Exponents in math are powers, right? When you think about it, actually, the word power has a lot of different uses in the English language. I just thought that was a cool way to start because that means nothing to our course, but we don't care about these definitions. Here's the definition I need you guys to know. From a physics and science point of view, power is the rate at which work is done. Power is the rate at which work is done. Yesterday, I wasn't able to be here. You were supposed to do some work. How powerful were you? Did you get a lot of work done or not? Right? I mean, I'm just kind of saying that in a silly sort of way, right? But from a physics point of view, power would be if you did a lot of work in a short period of time, right? Let's say that I asked you to do 5 tasks and you did them in 1 minute versus 5 tasks in an hour. The first one's more powerful because it happened quicker. Does that make sense? Power has a lot to do with like your velocity, your speed. Let's actually use that, speed. The speed at which you accomplish a task is power. Now, because of the fact that work is equivalent to energy through the work-energy theorem, it means that if power is the rate at which work is done, it's also how quickly energy gets consumed or used. And we often think of power when it comes to electronic devices. As a really basic example, most microwaves operate at about 1,000 watts. You ever seen that written on the side of an appliance or something, how many watts it is? A watt is a measure of power, and power is how much work is done or how much energy is used. And so if you have an electrical device that has a high power rating, it means that it's using a lot of energy, right? Classic example of this is light bulbs. Old-fashioned light bulbs, you know those like old-fashioned yellow-looking ones that, what do we call them, the incandescent ones? Yeah, the incandescent ones. They usually had a power rating of, say, like 150 watts. But newer light bulbs, you might be able to find a newer light bulb as low as, say, like 12 watts. And all that means is that it draws less energy. It uses less energy to accomplish the task. Okay. While I'm discussing this concept here, work being equal to energy is one of the 5 physics principles I need you to know at the end of this year. Okay? On that physics data sheet, there are 10 total. And I hope you guys take Physics 30, but even if you don't, of the 10 physics principles on there, you need to know 5 this year. 0 was uniform motion. 1 was accelerating objects. 2 is accelerating objects, but in a circle. Oops. One of them is the work-energy theorem. I think that one's number 3. And then conservation of energy is number 4 or 5 or something like that. So the work-energy theorem, though, is one of those physics principles that basically suggests that work is energy. So one last time, power is how much work you do as a rate of speed, or you can consider it as how much energy is consumed or drawn or used up or something like that, right? So the more powerful you are, the more energy you're going to require. Now I have a few other little notes down here I want to discuss. Note number 1, power is a rate of change in a similar way to velocity. Okay. We've done a lot of work this last year with graphs. And one of the best ways to kind of illustrate a graph is something like this. If I were to give you a graph of distance and time, oh, here you go. Thanks. Just close the door when you're done, hey? If I were to give you a graph of distance and time, what's the slope of that graph? Do you guys remember? Distance and time. If I were to ask you for the slope, can you do me a favor? Can you just close the door? Thank you. The slope would be the velocity. Velocity. Oh. Does that make sense so far? You guys remember doing that? Well, if I did the exact same thing, but rather than measuring distance versus time, if I were to measure how much energy you consume compared to time, the slope of that graph would be its power. Because the more energy that you consume, the more power you use. The less energy you consume, the less power you use. I want to just kind of illustrate how these graphs could possibly change. Let's say that I gave you a graph that was down here like the purple graph, and then I gave an alternate graph that was the green graph right here. In these three graphs right here, the green, the red, the purple, which one's traveling the fastest? Yeah, green's traveling the fastest. Why? Because it has the highest slope, right? And purple is traveling the slowest because it has the lowest slope. Is that hopefully somewhat familiar? Well, using that same logic, then if I were to ask you, if I were to draw three graphs of energy versus time, which one of these three devices uses the energy the quickest, you'd say, well, the green graph does, right? This green graph right here is sucking up energy like nothing else. And in an environment where not only do we have things like carbon taxes and gas prices being high, I would rather be the purple line, wouldn't I? Because the amount of energy that you use, I'd rather keep my energy consumption to a minimum rather than like plowing through energy with a very inefficient machine. Does that make sense? So I guess what I'm trying to point out is that in a similar way to distance over time being velocity, energy over time is power. Okay. Now there's one more note I have on here, but I don't think it's going to make a lot of sense, but I'll try it anyways. For anybody who, no one here is in calculus, right? Sometimes it happens. Whenever you eventually do calculus at some point, maybe you won't, you're going to talk about something called a derivative. Maybe you'll think back to this lesson and be like, oh, derivatives, rates of change. Power is a great example of what we call a rate of change. And so for anyone who eventually does calculus, you may see the overlap between this, but I think I'll move on because none of you are in calculus. When I used to teach at Walsh, sometimes I would have overlap actually of kids in physics and calc at the same time, believe it or not. So I'll just skip that part. Okay, here's our formula. These are the last formulas we're going to learn for our year. So after this, we're done learning new formulas. It's a fairly simple formula. In fact, it's actually even on the grade 9 PAT. I'm not trying to like shame you into being like, you should know this. I'm not saying that. I'm just trying to say you've learned this before. Somewhere deep in the back of your brain is this information, I'm sure. The formula for power that you would have learned in grade 9 is this. Power is how much energy you use over time. You also would have learned the formula power is current times voltage, but we don't even need that one. So anyways, power is how much energy you use over time, or what we can now do is say, rather than energy over time, it can also be work over time. That's our formula. It's pretty straightforward. Either use work or use energy. Pick one. So let's do an example. Suppose we have one of those really old-fashioned incandescent light bulbs, not very efficient, and it is a 150-watt light bulb. And you leave it on for 2.5 hours. Anybody here have parents who like walk around the house after you turning off lights? Some of you laugh at that. I've just realized I've become that parent now because like my little girls leave the lights on and I walk around and I go turn all the lights off because I'm paying for electricity. It costs money. Anyways. So let's say that you leave a light bulb on for 2.5 hours and you're wasting energy. You're wasting your parents' money or your money maybe. How much energy is being used? Okay. Pretty easy formula to work with. Power is equal to energy over time. So if you want to rearrange it, energy will be equal to power multiplied by time. Well, power is pretty easy, 150 watts. What about time, though? Do I just straight up use 2.5? Why not? Yeah, the standard unit in physics has got to be in seconds. So don't forget unit conversions. Times this by 3600. So where did I leave my calculator? Here it is. 2.5 times 3600 means that in terms of seconds, you've left this light bulb running for 900 seconds, 9,000 seconds, sorry. And 150 by 9,000 gives us this number here, 135,0000 joules. Over 1 million joules of energy being used by a simple 150 watt light bulb. Which is why your parents walk around after you turning off lights in the rooms that you've left. Anyways. Okay, a couple thoughts on this. One, we should do sig digs, because this isn't rounded appropriately. So 2.5 means I get 2 sig digs, so make it 1.4 times 10 to the 6 joules. For what that's worth, this is 1.4 megajoules. You guys know, like, 10 to the 6 being a mega? 1,000 of something, which is a 10 to the 3, that's a kilo. A 10 to the 6 is a mega. So you leave a lamp on with an old-fashioned light bulb in it with 150 watts, you've just used 1 million joules of energy. Now, that's my second point. That may seem like a really big number, but actually in terms of energy consumption, it's not. Ask your parents to look at like a power bill or something like that at some point in your lives, just so you can see how energy is bought and paid for. The standard unit of measurement for energy like natural gas is usually the gigajoule. Okay. Does anybody know what a giga refers to? How much is a giga of something? Anybody know? Fair enough. Okay. A kilo is 1,000. A mega is 1 million. A giga is 1 billion. So the standard unit of measuring usually natural gas and energy is the gigajoule of energy. So that's like 1 billion joules. So although this would be a waste of energy if no one was using the light bulb, it is actually still a pretty small portion of a gigajoule, which is the standard like amount of energy we measure stuff in. So does that make sense at all? In terms of what you need to be able to do, though, as long as you can use this formula right here and multiply these two numbers by each other, it's pretty straightforward. So. Okay, one last example then. Say there's a 200 watt motor and it's being used to lift shingles to the top of a roof at a constant speed. So I'm just going to draw a basic house here. Here's a house. Here's a guy on the top of the house going to do some work. We need a motor to somehow lift up all of these shingles because we need to get them on top of the roof. And I give you a 200 watt motor. Well, that 200 watts tells you how fast energy is being expended. 200 watts means that you use 200 joules of energy every second. Can I say that one more time? 200 watts means that every second you use 200 joules of energy. That's what 200 watts refers to, right? So basically, we get to have every second 200 joules of energy to help raise these things up here. The only other number I gave you, though, was a 28 kilogram mass. That's it. So you've been given a power number of 200 watts. You've been given a mass of 28 kilograms. And it's asking you to solve for a velocity. Where are we going to get a formula for this? Well, I want to show you a really cool trick. This is nifty. That's a good word to use. This is nifty. One of the formulas we learned for power is energy over time. But through the work energy theorem, power is equal to work over time. Everybody okay with starting there? Power is equal to work over time. The formula we learned today. What's work equal to, though? Work has other things it's equal to. Work is actually equal to force times distance. So if you'd like to, you can make the work portion of this formula. Oh, that's another P. Let me change that. My bad. The work part of the formula can become force times distance divided by time. And I'm going to be very purposeful with where I divide by time here. Because it's force times distance, that's work, right? And if I divide by time, but I put the time directly under D. Because this is kind of cool. This is literally like full circle. We started the year, and we're going to end the year with the exact same formula. What is D over T equal to? Velocity. Which means I can now make myself a new formula. Power is equal to how much force I use times by the velocity at which it's moving. Isn't that kind of cool how that works out? I don't know. Nifty was the word I used. I don't know if it's nifty or not, but if you guys would like to, write this down on your formula sheet. It's not on your formula sheet because there's kind of a quick little link to get there. But hey, if you want to write this one down, go for it. Because now we're ready to solve our equation. Wasn't the whole point of this to solve for velocity? Determine the velocity it's traveling? I now have a formula that involves velocity. So I'm going to do velocity is equal to power over force. Now, before I get to that, can I talk about graphs again for a bit? Just because that's such a useful skill. Hypothetically, let's say that I gave you a graph of distance over time. What was the slope of that graph? Velocity. However, what if I gave you a graph of how much power you used compared to how much force you used? What would the slope of that graph be? Also velocity. You kind of see how that would work? The way these slope graphs work is as long as two numbers are dividing by each other anywhere in your formula, as long as this top value goes on this axis, as long as this bottom value goes on this axis right here, if I were to give you a graph of two variables, if you find the slope of those two things right there, the slope is basically the two things divided by each other. So in theory, I could give you a graph of power and force, and you could find velocity. Or I could give you a graph of distance and time, and you could find velocity. I thought that was kind of cool. Okay, so back to our question here. We need power over force. The power value we were given was 200 watts. But we weren't actually told the force. So we got to think this through a little bit deeper. We need a force to pull this thing up, right? We need an applied force. What will that applied force need to be equivalent to or greater than? Gravity, yeah, right? Because isn't gravity what's keeping these things on the ground? So through like kind of a thought bubble process here of like this equals this equals this, we need to find this applied force, but the applied force better be equal to the force of gravity. Otherwise, if the applied force isn't bigger than gravity, then nothing's going to happen, right? So therefore, the force that we're going to use here will be the force of gravity, which will be mass times gravity. So it's going to be 200 divided by, what was that mass again? 28 times 9.81. Sorry, that's kind of ugly the way I drew it there, but now we'll have a velocity. 200 divided by 28 times 9.81, which is 0.73 meters per second. And now we know how fast this thing's moving. Yeah.
You made proof of the force of gravity. Wouldn't it be force of gravity going up, the force you're applying going down, and then wouldn't this be staying still?
Good point. Okay, so let's talk through that one for a little bit there. If we were taking it off the ground and we had the applied force exactly equal to the force of gravity, you're right, nothing would happen. But let's say that we got it moving a little bit, and then we made the two forces equal to each other. Through Newton's law of, like, first law of inertia, as long as it becomes in motion, this is how fast it would go, right? So you'd have to get it in motion first a little bit, but then as long as you made your applied force equal to your force of gravity after that, then it would just stay moving. Does that logic make sense? Yeah. But you're right. You'd actually have to give a little bit of an extra nudge to get her going at first, right? I mean, isn't that the same kind of logic behind like a car? As you're speeding your car up to highway speeds, your engine has to work a little bit harder, so your RPMs goes higher, right? But then once you're at cruising speed, right, all your car has to basically do is just slightly overcome the force of friction in order to keep going. That's kind of where you're at right here. Once you get this thing moving, so once you get the applied force moving, once it is in motion, all you need it to do is just overcome gravity, and it'll keep moving. Great question. All right. Any other questions on this? We're done. That's it. That's all I got. That's our year. So let's do a quick recap, and then I'll give you guys some time to work on stuff till the end of the class. First thought, let's do a quick recap of what you should have learned in the energy unit, because this is a short unit. I'm trying to explain my why to you as to why I made it so short. I put all of the energy stuff at the end because most kids find this the easiest. I'm sorry if you don't, but most kids usually do. It's also, in theory, almost review entirely from previous courses. Now, you may not remember your previous courses, but in theory, the curriculum calls for you to learn about energy in grade 10 and power in grade 9. So that's why I kind of like to leave this one for last. So quick recap. Here's some highlights of what you should know about. Highlight number 1. There are some formulas for energy you should be aware of. The kinetic energy formula, which is 1/2 mv squared. The gravitational potential energy formula, which is mgh. And the spring potential energy formula, which is 1/2 kx squared. Okay. All those formulas are in the same spot on your formula sheet. Okay. We talked about that on the first day of the unit. We also talked about one of our new physics principles, the work energy theorem. And the idea that if you're doing work, it comes at the expense of energy, so work and energy are basically the same thing as each other. The formula for work then is force times distance, possibly times by cosine of theta if there's a bit of an angle you need to account for. In this example right here, I'm going to assume that the force was pulling up and the distance was pulling up, but sometimes you can pull a direction and it can kind of like go off to the side, and so you need to use an angle once in a while, so that's where the cosine of theta comes in. But that was more or less our first lesson. 3 formulas for energy plus the work is force times distance formula. So that was lesson 1. Lesson 2, we talked about different types of systems. There's 3 types of systems. You probably learned this at some other point in your life, but if not, the recap is open systems, anything goes. Everything can go in and out. Closed system, now you shut the door. Matter can no longer go in and out, but energy can. The third system is what we'd like to assume, but they're pretty hard to get. An isolated system means that not even energy is lost, but usually energy is lost due to friction of some type. We just get to like pretend it doesn't happen. Conservation laws are then really important for isolated systems because that was our third lesson, which you need to watch that YouTube video. If you didn't watch my YouTube video on conservation laws, you really should. But the basic concept is if you know how much energy your system has, it should stay the same the whole way through. And so if you know you have kinetic energy and it's going to turn into potential, you can kind of make yourself your own equations. Making equations is always tough. So if you didn't read through and try like the 5-6 examples that I gave on conservation laws, you should. Okay. The final topic then was today. Once we understand that energy and work are the ability to accomplish a task, power is based on how well you do that task, how efficiently you do it. If you can run through 5 assignments in one day or 1 million assignments in one day, well, the second one was more powerful because you accomplished more, right? Either do more or work faster, but either way, that's what power is in a physics setting. Right? So we can either consider power to be how much work is done or how much energy was utilized. And I think that's about it. So, questions? Comments, concerns, conundrums? Okay. 2 passing thoughts, and then I'm going to shut up and let you guys either take off or do some work. It's one thing to have me show you some examples on the board, but that's not, to me, where the bulk of the teaching is supposed to come in. Although this was a me directly teaching you kind of lesson, you need practice, right? You can't just watch me do a few examples on the board and be like, yeah, I probably got it, right? So I cannot stress enough, try the practice assignment, okay? If you can. I get it, you're busy people, maybe you don't have time, you don't need to, but the answer key is online. Give it a try, even if you just look over the answers to the practice assignment and go, oh, okay, I see how you did that, okay? On Monday, what I'd like to do on the schedule, Monday, let's go over the assignment that is 4 marks. Let's talk through together as a class how to do that one. Tuesday, let's do a practice quiz. Let's see whether you get it or not. It's really important that you try the practice quiz. I feel like we've had some great learning moments after unit tests. Like when I sit at this whiteboard table and I go through with you how to do the unit test, and a lot of you go, oh, that was a bad mistake, or you learned something through that process. That's great. That's valuable. Let's do that after quizzes as well, though, right? You can do it by yourself, but that's why I've got a quiz scheduled for Tuesday so that Wednesday you have a day to kind of figure out, oh, that's where my mistakes are made, right? And then on Thursday we'll do a unit test. So that's thought number 1. Now, if you can, try to work on some of those tasks. Thought number 2, we're getting close to the end of the year. We still have kind of 2.5, 3 weeks left. I've passed back a whole bunch of work if you want to redo it. I have about 20 minutes left in class today. If anyone would like to go over some ideas on how to fix your most recent assignment that I passed back, maybe I'll work at the middle table here. And if anybody wants to come and join in there, you're welcome to. If you haven't done those assignments, you should, because 1, it helps your learning. 2, it helps your marks. 3, I told you to. I don't know if I have the power to tell you to do things. So, okay. Sound good? All right, I'm rambling. I'll shut up now. You guys are welcome to work on what you want, but if you want to work on the assignment, come join me at the middle table. So, hey Google, play B93.